Previously, this is a whole new mechanics for basic physics. Displacement in space only occurs with a displacement in the passage of time, acceleration. Though it may seem elaborate, it is consistent with the rest of physics.
Mass can be accounted for as being composed of three-dimensional time components and can successfully be applied to Newtonian mechanics.
Can this new concept of mass be applied to general relativity, shedding new light on the nature of gravity? Let's examine the application of these new concepts for basic physics to the Newtonian theory of gravity. Can we get a better understanding of what gravity is, assuming mass is a composite of time, as suggested? And, in doing so, can we gain some insight into possible deficiencies in the theory of general relativity? If acceleration is the ratio between two varying rates of the passage of time, then this must be applied to gravity in some sort of way. We could write something like this, where gravity would equal the ratio between two varying rates of the passage of time multiplied by the inverse square of the distance. But which distance? By introducing extra time dimensions, this whole gravity equation is going to change. But to what? In addition, where are the mass terms? The mass terms are partially represented through the relationship between t double prime and t prime. But since we simplified our equations, setting the relation terms to 1, we can bring them back into the equation, placing an emphasis on their relations. Since we are using temporal mechanics to define our mass and acceleration terms, we will use the relation terms big N and little n with the following equation for gravity, where t double prime over t prime is the ratio between two different passages of time, acceleration, corresponding to the relations of big N and little n, and where big N together with little n is some complex vector field representing the entangled relationship between big N and little n, with t squared as the period of time multiplied by a series of present moments of the event, quantity squared. It has previously been shown that the existence equations account for infinite regression and infinite progression of relative frames of reference using a set of continued fractions. These equations infer multidimensional time and can be transnumerated into a three-dimensional time coordinate system. When these equations are plotted within a multidimensional time construct, it becomes apparent that the slope angle of ordinary linear time and the slope angle of relative time are equivalent, using infinite series of non-inertial frames. This applies to the concept of the identity constant, where if a over b equals 1, then I equals 1. If a over b does not equal 1, then I is greater than the identity constant. Looking at acceleration plotted within a three-dimensional time construct, we can see that the same equivalence principle applies. What this suggests is that acceleration can be reduced further, consisting of relative frames of reference, specifically a relative to a relative to b relative to b, and b relative to a, and that the relationship between these four reference frames can be used to further understand what mass and acceleration are.
In 1634, the Inquisition sentenced Galileo Galilei to house arrest for heresy. His crime? Heliocentrism, believing that the Sun is at the center of our solar system rather than Earth. It was during his house arrest that Galileo made his greatest contributions to physics. Through his many observations of time intervals, dropping various weights, rolling balls down inclined planes, examining pendulums, and so on, Galileo made a great discovery. horizontal motion and vertical motion are independent. Galileo noticed that all objects appear to fall with the same acceleration, independent of the mass of the falling object.
In our example here, we have two pendulums with a length of 60 centimeters and a bob mass of 500 grams. One pendulum is displaced 10 degrees from vertical and the other 25 degrees from vertical. Releasing them at the same moment, we can see they maintain the same rate or period. The size of the swing doesn't matter. Scientists call this property isochronism. In 1610, Galileo wrote, "The marvelous property of the pendulum is that it makes all its vibrations, large or small, in equal times." The next surprising attribute of the pendulum has to do with the mass of the bob. Will increasing the mass of the bob change the period of a pendulum? Again, we can set up a simple experiment. One pendulum will have a mass of 500 grams, the other double the mass at 1,000 grams. This time we will control the length of the pendulums at 60 centimeters and the displacement at 25 degrees. Releasing them at the same moment, we can see the period remains the same. Surprisingly, the two bobs, though of different mass, swing side by side, maintaining the same period. The heavy bob moves at the same rate as the light bob. This may be the revelation that led Galileo to challenge the teaching that heavy objects fall faster than light objects.
Newton furthered Galileo's observations, formalizing a mathematical system proving that projectiles, such as cannonballs, and celestial objects, such as planets, all follow the same set of mathematical laws. Einstein later refines this equivalence principle between gravitation and acceleration in his theory of general relativity.
However, a question can arise whether or not Galileo was correct. Did Newton and/or Einstein overlook anything, accepting Galileo's conclusions at face value? Since mass is related to gravity, proportionally, it would seem that heavier objects fall faster than lighter objects.
So the standard misconception is to believe that the black ball will accelerate at a greater rate and reach the ground first. Many people had an idea that both balls would land at the same time, but they didn't know exactly why. Many people seem to think that as an object falls towards the Earth, it falls with a constant speed, because they knew both balls needed to reach the ground at the same time, so they reasoned that the force on them must be the same.
However, countless sophisticated experiments have been done to demonstrate that this is not the case, and that different objects with different masses, dropped from the same height, fall with the same acceleration, landing at the same time. This is important because it relates to other conservation laws. This can seem counterintuitive because reasonable arguments can be made that heavier objects fall faster, or vice versa. For instance, an object as massive as a planet should fall towards the Earth faster than a significantly lighter object, such as a feather, since mass is proportional to gravity. So do objects with a significant difference in mass fall at the same speed or not? Though physics seems to have sealed the door on this issue, a re-examination of the equivalence principle using three-dimensional time can reveal how and why intuition and observation conflict with respect to this principle. Here are the possible ways to answer this question. 1. Heavier objects fall faster than lighter objects, and 2. Lighter objects fall slower than heavier objects. Since gravity is proportional to mass, more massive objects have more attraction than less massive objects. 3. Heavier objects fall slower than lighter objects, and 4. Lighter objects fall faster than heavier objects, since massive objects take longer to start moving and lighter objects are more easily moved. 5. Heavy and light objects fall with the same rate of acceleration, independent of their mass. What was not available to Galileo or Newton was Einstein's theory of relativity.
Albert, standing still in space, flows through time, so that a vertical line represents a fixed point, while a horizontal cross-section represents simultaneous times in different places. The same idea can be used to show the relativity of time. When Henry and Albert observed the same expanding light sphere, it reaches their detectors at definite points in time and space. These are called events. The light itself traces out a cone. To Albert, events on the horizontal cross-section are simultaneous. For him, one of Henry's detectors flashes first. Then both of his own flash simultaneously. And finally, Henry's other detector flashes. So he thinks these two events are simultaneous. But Henry thinks these two events are simultaneous. For Henry, simultaneous events take place everywhere on a tilted cross-section. So he thinks one of Albert's signals goes first, then both of his, then Albert's other signal. If Henry were drawing the picture, he would draw his lines of constant place and constant time perpendicular to each other. That wouldn't change the light cone at all.
Putting units of measure aside for a moment, there is a particular way to resolve the issue between intuition and observation. Assume that from a particular frame of reference, more massive objects fall faster than less massive objects. We can assign this concept to a position frame of reference. However, we can conveniently appeal to Einstein's idea that a stationary object moves through time at the speed of light, and that when an object moves through space, it loses some of its relative time to outside observers.
That guy over there would say that I'm not moving at all. But I am. I may not be moving through space, but I am moving through time. And as long as I'm standing still, that is, not moving through space, Einstein said that all of my motion is through time. But look what happens if I walk toward that guy. We've exaggerated it, but because I'm now in motion, he'll perceive my watch ticking slower. That's because, from his perspective, some of my previous motion through time is being diverted into my motion through space. If we really exaggerate the effect, he'd perceive all my movement, my voice, everything about me slowing down. And now that I've stopped moving, the passage of time on our watches once again agrees.
We can assign this concept to a momentum frame of reference, assuming that there is an inverse proportional relationship between these two frames of reference. When superimposed together simultaneously, the heavy and light object both fall, on average, at the same rate. This would satisfy both intuition and observation. So apparently the correct answer is actually all of the above. This is an entirely new approach to the equivalence principle. Not only is this consistent with Galileo, Newton, and Einstein, but it reinforces a link between physics and the equivalence principle found in existence. Additionally, we will see that this becomes the place where general relativity and quantum mechanics merge. We saw that if the absolute value of the difference between two forces is equal to 0, then there is no displacement. Inversely, little n times t double prime and big N times t prime tend to move towards inequality or equilibrium. The proportionality between the inequalities of t double prime over t prime and big N over little n is an integral part of the mechanism of gravity based on temporal mechanics. How do these mechanisms work?
When two or more particles interact, their wave function becomes entangled in such a way that some properties of each are now depending on what happens to the other particle. Then these particles can be carefully separated while in careful isolation to distant locations. But as long as they're not disturbed, they are still entangled and still have properties dependent on each other.
The bizarre phenomena of the quantum world, action at a distance, can account for the mechanism of gravity when the inclusion principle is included within the definition of quantum entanglement. What is quantum entanglement? Fermi particles, such as electrons, can only be in very distinct states, such that once one state is occupied by one Fermi particle, that state cannot simultaneously be occupied by an additional Fermi particle. This exclusion principle is what gives diversity to the elements and the rigidity to matter. Quantum particles affect each other's quantum states based on this principle, and distance appears not to be a factor, hence, action at a distance. What if we modified this concept, allowing for a slight exception to this rule, the inclusion principle? Without violating the rules of physics, quantum entanglement can be used to account for gravity in the following way. If two particles are in the same state at the same time, and it is not possible for them to change state in order to avoid violating the exclusion principle, the identity of each separate particle can become indistinguishable, resulting in just one particle. If the two particles become one, what happens to their mass? What do we do with the excess mass created by this identity crisis as not to violate the conservation of energy? One of the masses is converted to a relative time and conserved through a change in the rate of the passage of time. The gradient of change in the rate of the passage of time of the massive object is the gravitational field of that massive object. Now, the two particles, as one, exist in a slower frame of reference than before. In a three-dimensional time way, the two particles remain both separate and together simultaneously, a superposition of possible states, where the initial separate states are the probability of the single state in reverse, and the single state is the collapsed wave function of that reversed probability. The particles become indistinguishable, and without violating the conservation of energy, the two become one, with a probability of having been one or the other of the two interfering particles. The exclusion principle prevents the inclusion principle from collapsing the wave function into the same space at the same time, and the inclusion principle prevents the exclusion principle from distinguishing between particles. This apparent paradox results from limiting physics to one time dimension. More than one Fermi particle can exist in the same place at the same time, depending on what you mean by time. Each particle is distributed to different present moments corresponding to different rates of the passage of time during the same period. The more particles sharing the same states, the more distribution through different present moments at varying rates of the passage of time occur during the same period of time. This is why a point particle mass, or the center of mass reference frame, can be used to calculate the motion of masses. Spatial extension is not a necessary component of mass. Mass is composed of temporal coordinates. Revisiting the temporal definition of mass, we find that the passage of time coordinate t' and the corresponding relation term n have an inverse proportional relationship not dependent on the linear time vector t squared. The linear time vector is composed of two coordinates, period t sub 1 and present t sub 2. Since particles can exist in the same place at the same time period by being distributed throughout various present moments at various rates of the passage of time, these quantities associated with particles' masses would be distributed along various present moments, leaving the period and spatial coordinates unchanged. In other words, the period coordinate t sub 1 and the present coordinate, t sub 2, can vary inversely proportional, not affecting the value of t squared. However, since we are dealing with various rates of the passage of time, differing mass distributions of point particle masses, the difference in the passage of time between various masses in different locations will displace the center of mass towards equilibrium through uniform invariant motion, inversely proportional to the distance and proportional to the period of time the motion takes place in. We know this simply as gravity. Identity crises, IDs, occur between the constituents of big N and the constituents of little n. The exclusion principle dictates their distance. The inclusion principle dictates their proximity. As time goes on, IDs occur proportional to the total number of constituents of both big N and little n, inversely proportional to the distance, with a change in position between big N and little n for each ID. If the number of IDs increases with time, then big N and little n will begin to merge towards being one. If the number of IDs decreases with time, then big N and little n will increase with distance. If the number of IDs remains constant, then little n will move in uniform motion around big N. Returning to the inversely proportional relationship that both space and period of time have with the passage of time, and the Lorentz invariant relationship between space and periods of time, we can find deeper insight into the Galilean equivalence principle. What becomes apparent is that these four potential relations between space, linear time squared, and passage of time have a complex conjugate type of relationship where, relative to the lighter mass object, we get the following frames of reference, and relative to the heavier mass object, we get these frames of reference. From here, we can derive two equations for acceleration, one relative to the falling object, the other relative to the massive body. What we can see is that these two equations are conjugates. Therefore, both masses are experiencing the same acceleration, though not in the same way. The new definitions of mass and acceleration are consistent with and reinforce Einstein's equivalence principle.
From the center of mass frame of reference, point particle masses have a probability of being located at each separate mass position in spatial and temporal coordinates, proportional to the mass ratio between the masses. Through an action at a distance, the inclusion principle and the exclusion principle set the perimeters of quantum entanglement, where the inclusion principle represents the probability that all the mass is concentrated into a single point, and the exclusion principle represents the probability that all the mass is separated into distinct points, all proportional to the separate distributions of mass and inversely proportional to the square of the distance between them. The larger mass has a larger probability density of time, and the larger mass exists slightly farther in the past relative to the smaller mass. The smaller mass has a smaller probability density of time, and the smaller mass exists slightly farther in the future relative to the larger mass. So that the masses can interact separately in equilibrium, sharing some rate of the passage of time, the lighter mass must be accelerated proportional to the square of the distance, so that the passage of time relative to the smaller mass can slow down towards the same passage of time relative to the larger mass. When two separate masses are in a free fall towards some large third mass, the same principles apply.
Well, in my left hand I have a feather, in my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon? And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
How does all this apply to general relativity, the Big Bang, the inflation period at the beginning of the universe, dark matter, and dark energy?